Hey, my name's Adam, and this is our sixth and final project. The song you're listening to right now is Music Sounds Better With You by Stardust. The pulses you see in the background are our audio visualization of the beats in the music. The red bars are the spectrum of the music's frequencies. When we started this project, we wanted to figure out how to actually extract this data from the music, so we started by using some filters. We started with a low-pass filter, finite impulse response low-pass filter, that is. The equation can be seen here, where y of n is the output signal, x of n is the input signal, m is the number of terms, and v sub I are determined coefficients. These coefficients, because we wanted a low-pass filter, are in the form of sync functions. We used two filters to try different things, and the first filter only has 10 terms, and the second one has 50 terms. As one would expect, the 50-term filter actually turned out to be a much better low-pass filter, because you can see in the frequency domain there's the sharp cutoff after allowing some low frequencies through, and the high frequencies are fully cut off. With 10 terms, there's a sloped one, which is not fortunate. There's a high frequency component as well, because the fast FFT is symmetric. So when we applied these filters, we got the following information. The blue here is the original audio signal, the red is the poorly filtered one, and the green is the well-filtered one. As you remember from the equation earlier, there was an x minus I term, which means that we were using past information, which means that there would be a time delay. So you can see with the 50 terms, there's actually a larger time delay. But it is a better filter. So if you look at the spectrum samples that we have as well, then you can see that in the normal signal we have a lot of frequencies, whereas in the well-filtered one there's a sharp cutoff at our cutoff frequency, which was 5,000 hertz, excuse me. With the crappy filter, you see a sloped cutoff, as we expected. We didn't end up using this because we found a better way to do visualization of the beat, which will be explained later.
Hello. Let's talk about how we cut off bits of music, like the one we used here. So if we just take a sample and cut it off squarely on each end, we get a rectangular window, which you can see on the slide here. A rectangular window has these sharp edges. Now, sharp edges in the frequency domain have essentially infinite frequency, and you can see this as ringing here in the transform of a rectangular window. So to avoid this problem, what we do is we use something called the Hamming window. The Hamming window is designed so that the amplitude of the closest peaks to the one we actually care about is lowest in comparison to our main peak. Now here you can see the signal of our sample of Stardust French house classic Music Sounds Better With You. You can see there are pretty heavy bass beats coming along. And here is a spectrogram, so we have frequency on this axis and time on this axis. Now, an interesting thing to note is that if you looked at this file, you would think it's sampled at 44.1 kilohertz, giving us a maximum or Nyquist frequency of 22 kilohertz. But if you look at the spectrogram, there's a pretty hard line here at about 19 kilohertz. So it looks like there's only noise above that. It looks like what happened was this was sampled at a lower rate and then upsampled later.
So as you saw, the background of the visualization pulses to the beat. And the way we found to do that was to use a similarity matrix. So the idea was that if we window our time domain function into smaller windows, each of those windows is a one-dimensional vector. And you can find the similarity of one-dimensional vectors by taking their dot product. So here, the similarity of window I to window j is defined as the normalized dot product between them. So when we took the dot product of every window with every other window, we got here the similarity matrix, where both axes are the samples of the signal. And as you can see here, these squares show the similarity, where white means completely similar and black means not similar at all, so there's a white line through the diagonal where the signal is identical to itself. So the way we use this was when we found the similarity of the self-similarity matrix with itself, we did this by the autocorrelation, which is here and is very similar to a convolution. And this allowed us to basically sum along the diagonals so that when the self-similarity matrix overlapped with itself as it was offset in time, we could find where the diagonal sum was the greatest, and that was how we pulled the beats out of the sample, where the self-similarity matrix overlapped with itself when it was shifted in time. And that's how we got the background to pulse to the beats.